Hey, what up, y'all? Shout out to my second hour. What up, peeps? We're going to be talking about some continental. We've been talking about it, this idea of the continents that they have not always existed in these places that they are today. A guy by the name of Alfred Wegener in the 1900s theorized that the continents were once joined and have moved apart over time. But he wasn't able to theorize, he wasn't able to understand what caused them to spread apart. So he was widely laughed at and thrown out of the scientific world because this was just an absurd kind of thought that these huge masses could move over time. Right? He called his theory continental drift and used evidence like matching continents, continent edges, similar rocks, and fossils to now that are now separate. So when we talk about South America and Africa, right, the puzzle pieces kind of join together. They look like they could be next to each other. And he also saw that the species on the west side of Africa and on the east side of South America were similar, if not identical. How did that happen? Well, over time, he said that those were at one point touching, and then over millions and millions of years, they spread apart. But he really had no mechanism. What was causing them to spread apart? His theory was that they did at one time. Okay, but he unfortunately had no theory on what caused the movement. So let's take a look at another video on continental drifting. Let's take a look. This is 65 million years in a minute and 20 seconds. Okay, and so it's going to show you kind of a theory of where we were and then what's the future ahead of us looks like.
You think you know me? I can talk at anyone, anything, anywhere.
The reactor was a rehearsal. Who knows what he's cooking up next?
Locate this guy right now.
If a guy this dangerous, it's all about if I can get close enough, fast enough.
Black Hat starts Friday. Rated R.
$4 million years ago, right, these land masses are moving in and out, banging into each other, creating mountains, destroying mountains. This is all theory. We don't know this for sure. Now we start to see things that are familiar, right? South America, Africa, okay, to our current location, 50 million. Now we're going into the future, 50 million years. This is what, if they continue on their same path, where we think they will be in 50 million years. 150 million years into the future. Antarctica goes bye-bye. South America starts coming down south. $250 million years into the future. So that's the theory of continental drift. Okay, we know now that Alfred Wegener knew exactly what he was talking about, right? Because we have direct evidence that supports his theory of continental drift that he did not have in the early 1900s. Okay. In the 1950s, Harry Hess theorized the seafloor spreading, explained how continental drift occurred. Seafloor spreading, so the bottom of the sea, the oceanic crust, the bottom of the ocean is spreading apart, and that's really what his theory was talking about. And this is based on the discovery of the mid-ocean ridge, right? Down the Atlantic Ocean, there's a huge ridge that runs almost from the Antarctic all the way up to the Arctic, all the way up to the North Pole in regions. And by discovering that, we found out that these portions of the floor were the iron in the magma as it cooled align in opposite directions of our magnetic field is today. And they found out that there were series where the magnetic poles were reversed. And that helps explain this idea that the continents are spreading apart. We'll move more into that, but this is in the 1950s, so it's well after the Alfred Wegener theorized continental drift. Okay? We know that they're put together like a jigsaw. They're like ice floating on top of water, but they're a jigsaw puzzle. Okay? The crust is like a cracked egg, and it all fits together like a jigsaw puzzle. We call those pieces tectonic plates for a few different reasons. But these are the main, I've outlined in black, the main plates that we know of today. Right? We've got some smaller plates that I've outlined as well, but we've got huge, the red names are really the large plates that exist today. What fuels this movement? Okay? Because we thought these are so massive, they have to be just sitting in place. Right? They can't be moving. Well, we figured out that they are. Right? The convection of the liquid mesosphere causes the parts of the crust to move. Right? We've talked about this. The mesosphere is a liquid rock, and hot portions of it, places where it's really hot, it's going to bubble towards the surface or towards the crust. And in those places, it's spewing magma into or onto the crust, and then that magma is solidifying into new igneous rock. And then there are other places where the mesosphere is cooler, and so it begins to sink towards the core. The core of Earth is really what's driving that heat source and heating the magma. And as it heats, it goes towards the crust. And then as it gets towards the crust, it starts to cool down and sink back towards the core. And it's this vicious cycle of convection currents. Okay? Ridge push occurs where the magma is rising towards the surface or towards the crust. Right? It starts to push the ridge or the plates in opposite directions. Right? Where magma forces cooling floor away from downhill towards the ridge, from the ridge. Okay? So this mid-Atlantic ridge is this mountain range underwater that spews lava, and then that lava freezes into igneous rock. Right? And then we have on the other side of oceanic crust, we have slab pull, where the slab is being pulled down into the mantle. And that's where we have what's called subduction. Right? These subduction zones occur when gravity and the plate's own weight pull the plate into the magma. Okay? This is a picture in your book, right? Mid-ocean ridges of seafloor spreading, 243 and 244, also on Google Earth, right? So ridges in the oceanic crust where two plates are spreading apart. Mountain ranges are formed. So they're underwater mountain ranges all the way along the mid-ocean ridge, right? Magma spews from these ridges and hardens into newly formed rock and pushes the two plates apart, right? So we've got ridge pull right at this location, and then on the other side we have the slab pull, which is pulling it down into the mantle. Right at the top of the mountain where the magma spews out, we have what's called a rift or a rift valley. Okay? So that rift is where one plate is moving in one direction, the other plate is moving in the opposite direction. And then we have this mid-ocean ridge, which is the mountain range underwater, and then the oceanic crust. The rock closer to the ridge is younger, and the rock further from the ridge is newer. Right? So as this spews out and hardens, right, this eventually will move away, right, when new rock spews out and hardens, and then new rock spews out and hardens. So as you get further from the ridge, the age of rock gets older and older and older and older. If I'm going towards the ridge, the age of rock gets newer, newer, and newer, and newer, all the way up to the rift, where that's brand new rock that was just formed. How fast are they moving? Not very fast. Okay? But if we look at this over 50, 100, 150, 250 million years, right, this continent that we are on right now will move centimeters a year. Okay? And how do they measure this? Well, they measure this by taking the distance and dividing it by the time. Okay? So we take the speed at which a plate is moving, and we calculate the distance and we divide it by the time. Okay? Now, here's a picture from Google Earth. You can do that. You can look it up, Google it. Mid-ocean ridge. You can see, not very well on our picture, but I'll pull this up in class as well. But you can see that there's this this ridge that runs the entire length of the ocean floor. Okay? And what we see is just what I was explaining here, right? The green is new rock up here, right? Spews out and hardens into new rock. And then over time, new rock spews out and hardens, and it pushes the green outwards. And then new rock spews out, it pushes it further and further out. That is what's called a divergent plate boundary. Divergent in opposite directions. Very much, and we're going to talk about that later on. All right? Peace out, homies.